Time-appropriate greetings, ladies and gentlemen. This is Sean McBride, your graduate teaching assistant, and I'd like to welcome you to Laboratory 6. Today I don't have terminal-based slides for you. I've unfortunately only got PowerPoint. So sorry about that. But today we're going to be covering or extending our coverage of the pthread library and talking about a new construct called the condition variable. Over the past couple of weeks, we've covered how to create threads, how to join on exiting threads, how to use mutexes to achieve mutual exclusion of critical sections, and the new capability that the condition variable set of APIs provide is a way that you can basically wait for a particular condition, and while you're waiting, to actually put your thread of execution to sleep. Programmatically, you can accomplish the same sort of logic waiting for a particular condition using just regular old mutexes, but to be able to do that, typically you have to do busy waiting. So there's some sort of while loop, and then you basically have to spin waiting for the condition before you try to take the mutex. So that's a high-level difference between the mutex and the condition variable. I want to walk through at a high level how this works, where some of the pitfalls occur with condition variables, because there definitely are some serious foot guns here. And then I'm going to basically give a brief demonstration using a Pokemon-themed example I threw together to just kind of show how this all looks with code. All right, so imagine that we have started a C program, and that C program has started running our main function. And within that main function, we create three new worker threads. So inside of some sort of for loop, we loop through and create worker thread 1, 2, and 3. At this point in the system, we have 4 threads of execution that are active. And then the worker threads begin to execute the function that we passed to pthread create. And in this case, that function begins to invoke some condition variable APIs. So worker thread calls a new API that you're probably unfamiliar with. It calls wait. Let me think about that. Pthread conned wait. So worker 1 calls pthread conned wait, and what that does is it puts that worker thread on essentially what you can kind of think of as a sleep queue. And what that means here is, since this condition variable queue is empty, worker 1 is now at the head of the queue, and once it's on the queue, it goes to sleep, hence the sleep queue. So the rest of the workers have the same created in a for loop with using the same function as the entry point for their threads. So they execute the same logic. Worker 2 calls wait, gets added to the queue associated with the condition variable, and goes to sleep. Worker 3 calls wait, gets added to the same queue, and then goes to sleep. And so at this point, even though we have 4 threads, 3 of them have yielded the processor indirectly through this condition variable API, and they're sleeping. So the only one that is still remaining in executing is the main thread. And the main thread is able to make API calls on this condition variable, and that affects basically what happens to all these sleeping threads on the queue. And so one of the options is broadcast. And broadcast, as you can probably imagine, means that main sends a single API call, and that API call cascades through the entire broadcast domain, which in this case is constituted by all of the worker threads that are on the queue associated with the condition variable. And within this broadcast domain, essentially all of these threads are woken back up. And so we end up eventually in a situation essentially like this. There are some additional complexities that have to do with essentially the lock that's associated with the condition variable that I'm just going to ignore for now. The second option is signal, and so this is a more granular option where the main thread can signal the condition variable, and that results in the thread that is sleeping at the head of the queue being woken up. So here, in this case, it's worker 1, and we can see that worker 2 advanced to the head of the queue. And we could imagine that main could call this 2 more times, and the end result would be, again, 4 threads, sort of similar to the broadcast. Our third option is deadlock, unfortunately, and I'm going to walk through an example of how this could happen. But generally, when you work with some of these more advanced pthread APIs, there's a lot more struggle getting all these patterns right. So when you work through this lab, just understand that you're probably going to hit some of these race conditions and potentially deadlocks, and that's okay. That's okay. Generally, taking a step back and kind of thinking about the flow of execution of the threads, potential interleavings, and potential timing issues can help with that. So I'm going to go through just an example of a way that this could basically misfire. So as before, we started our program, and main is executing and is the only thread of execution in the virtual address space. Main calls in a loop pthread create, which creates 3 workers that are all executing the same function. And as before, worker 1 calls wait and then goes to sleep. Worker 2 calls wait and then goes to sleep. And the difference this time is that before worker 3 calls wait and goes to sleep, actually the main thread calls broadcast. And so the result of this is that probably we've coded this logic up thinking that when main calls broadcast, all of the workers would receive this message. That's not necessarily the case. So in this case, only 2 workers were successfully able to make it on to the queue associated with the condition variable and are thus in the broadcast domain. So main calls broadcast, only worker 1 and worker 2 receive that, and they wake up. But then worker 3 calls wait and goes to sleep. And we can see by that little spinning top, main is at this point spinning, waiting for 3 workers worth of work to complete. And that's never going to happen because the 3rd worker is sleeping. So this is how we end up basically in a deadlock type situation. Alternatively, main could have itself slept, expecting that the 3rd worker would signal that it should wake up. And so there's a couple of different ways that this could happen, but essentially the problem is assuming that all the workers have made it onto the condition variable and waited when in fact something is still actually executing and live and thus misses the signal. So here's just kind of a summary of the problem here. A worker doesn't enqueue in time, it misses the signal, and it ends up waiting indefinitely, and then we end up potentially having a race condition. So I'm going to walk through a couple of just code examples to show what this looks like. All right, so this example, as I mentioned before, is Pokemon themed. Within Pokemon.c, I have just essentially a really large array of all the different Pokemon. And we have a random function that gets a random Pokemon. And I've got some sort of off by 1 error I noticed based on a previous run of this, so maybe I only have 149 Pokemon in here. I'm not totally sure. But in any case, let's walk through the first example. So in terms of global state, we have an array to store our thread IDs. And we have basically two condition variables here, but I think we don't use the second, so let's just go ahead and delete that. Okay, so we have a condition variable called trainers, and that condition variable has a mutex associated with it called trainers lock. We have some arrays, and the elements map one-to-one to threads. So essentially the first thread has access to it, or the first thread represents the Pokemon trainer named Ash and stores the random Pokemon in this first element here. The second thread is Misty, and she has access to this element here to store her random Pokemon, etc., etc., etc. So that's our global state. Going down to main, we basically seed our random number generator, and then we create our threads. In this case, we've got 5 threads. We call thread main. So let's pop up in thread main. Thread main is receiving as an argument the trainer ID, and just by virtue of the somewhat gross pthreads API to be able to pass a integer, we have to cast it to a void pointer to be able to pass by value. And you might notice I'm using this int64 value, and this is an important choice because if I wanted to do something like int32t and I tried to cast a void star, I would actually get some errors here because the width of those two data types are different. So on a 64-bit architecture, the pointer is 64 bits, and that means that if we want to pass an integral value, we want to use something with the same width as the machine architecture. So that would be something like a uint64 or an int64. And in this case, I'm using the int64. So we pass the trainer ID in here. And again, that's 0, 1, 2, 3, or 4. Our thread takes the lock and then begins a loop and then immediately calls wait. We need to basically take this lock to be able to call this condition variable, right? And so once this condition variable is called, the thread is added to that wait queue that we saw in the PowerPoint, right? Like here, and then goes to sleep. So all these threads stop right here and they wait for some additional action. And we can go back to main to see what happens next. So after pthread create, essentially the main thread begins to execute a series of rounds. And to do that, it calls pthread cond broadcast. And we saw what broadcast does earlier. That essentially sends the signal to wake up to all of the threads that are waiting on the condition variable. And then we sleep for 1 second. So I'll go ahead and make this and execute the program. We can see what that looks like. Okay, so we can see each round, all 5 of the Pokemon trainers take a random Pokemon. And we run to completion and exit. One thing I saw in previous lab groups is that there was a lot of confusion about this life cycle for this thread. And mostly it's kind of thinking through, well, doesn't the thread have to exit at some point in order to be joined? And in fact, we do have a pthread exit, but we have an infinite loop here. And because of that infinite loop, this stuff below here never actually gets reached on line 36 and 37. And that's honestly okay for this example because we saw basically this loop runs for 10 loops, and then the main thread calls exit. And when any of the threads use exit, that actually exits the entire process, which terminates all of the threads in that virtual address space at that point. So that's why we don't necessarily need a particular exit logic here, and that's why this actually never gets called on line 36 and 37. Okay, cool. So I want to show a couple of things here. So first, we talked about signal versus broadcast, and I want you to go ahead and think, if I basically swap out these two calls on line 56 and 57, and I comment out broadcast, and I uncomment signal, and I recompile and execute, what do you think is going to happen? Go ahead and pause and think about that for a moment. Okay, got a hypothesis, I hope. So I will recompile after saving. Okay, and I will re-execute. And we can see that only one Pokemon trainer selects a random Pokemon each round. I think that's pretty consistent with what we talked about on the slide deck. The signal only impacts the thing at the head of the queue associated with the condition variable. And that's why we can see, if we look at the order here, it's essentially consistent with the order of our trainer names, which is consistent with the order of the threads that were created first. Okay, cool. So let's go ahead and comment signal back out and uncomment broadcast. And this time I want to comment out this sleep here. You might be kind of wondering why this is here. And if I comment this out, we actually impact the order that the different threads run quite a bit. So in this case, the main thread runs quite a bit faster, and this loop here runs quite a bit quicker. Go ahead and just think how that might impact what we're going to see on the command line. Go ahead and pause. Okay. Let's run the experiment. Okay, interesting. Well, first we saw the program ran a lot quicker. We can see that some rounds had no trainers whatsoever. Some had 2, some had 1. We can see the order is a little bit more surprising. So previously we saw that the order basically was going in order of the trainers here. Ash, Misty, Brock, Jesse, James. And here we see Ash, Misty, Brock, Skip, Jesse, and James. And then we got Ash again. And so it's a little bit more interesting and random. And so essentially what's happening is this thread is calling broadcast faster than the threads can make it through the loop here. Right? So lines 29 to 34 takes a little bit longer to run than lines 55 through 58 after we comment out the sleep. So it's a little hacky to inject arbitrary delays inside of our code. I mean, it does happen in concurrent software sometimes that people do that, but surely there's got to be a better approach, right? And I've got a couple approaches that I can show you. So one idea that we might have is potentially trying to use a condition variable on both sides. So previously we had this trainer's condition variable, and now we have a new condition variable, gym leader. And the only thread that actually sleeps on that gym leader condition variable is this main thread, right? And so now we have both a broadcast on the trainer condition variable, and we wait on the gym leader condition variable. And if we go to the threads, we see we now have both a wait and a signal. And the logic for this is a little tricky because the main thread wants to call broadcast, right? And that broadcast is more than one thread. But we want to make sure that within each batch, only the signal back to the main thread is only called once, right? And so we have this kind of modulo logic here to make sure that it's basically the last thread to pick the Pokemon that calls a signal. And that guarantees that the batching kind of works as expected. So let's go ahead and compile and run this. Okay. And it looks pretty good. And that ran pretty much instantly. So quite a bit better than having that arbitrary sleep here. But we still have some potential race conditions here that may not be immediately apparent. So if I uncomment this sleep here, we essentially still have the potential where this is kind of similar to what I showed in the slide deck, where one of the threads can basically not make it onto this wait before the main thread calls broadcast. And in this case, this is pretty catastrophic because if all of our threads aren't on this wait and one of them misses the broadcast, we won't actually have enough threads run to be able to call this signal for the main thread, and this results in the deadlock. So I've uncommented this sleep here, and we can compile this and run. And pretty much right away we hit that deadlock condition. So that's pretty terrible. And what you might find is as you kind of add complexity to one part of your concurrent software system, you end up, it's sort of like shifting the race conditions to other parts of your code base. So this cycle of like identifying a race condition and then fixing it, and then that kind of triggering another race condition can happen a couple of times. And I'll just go one layer deeper just to kind of show one sort of escape valve for a situation where you're not able to identify all the race conditions. And that's to use an alternate API, which uses sleep, but kind of puts an upward worst case scenario bound on how long you're willing to sleep. And if you blow past that bound, it causes you to automatically wake back up. And that can kind of help diagnose what's going on. And so in toCond wait, I've done that. I have changed the pthread cond wait call to pthread cond timed wait. And the key difference here is now I'm passing this timestamp. And I don't really want to dig in too much, but this timestamp isn't a relative amount of time, it's an absolute timestamp. And so we actually have to kind of construct an absolute timestamp at some point in the future, which is a little bit gnarly using POSIX APIs. So basically we're saying in 2 seconds in the future, if something else hasn't woken me up already, just go ahead and wake me up as a fallback. And so now, if I invoke this, we can see we're hung, but then we hit the timeout. And even though obviously there's a timing issue, based on how much we're hitting that kind of timeout, we're still making forward progress. So we're never totally deadlocked, which is quite a bit better. Like slow is better than nothing, right? So that's all I really want to show in terms of these pthread condition variables. Let's go ahead and go over to the coding exercise that you're going to be working on. And so this exercise is quite a bit different. And to some degree, this is a simplified exercise, which previous lab groups have found a little bit challenging just because of some of the limitations on how this works. This exercise, the goal is to use a Monte-Carlo simulation to estimate pi. And if you're curious about the math behind that, looks like this is kind of a cached older version, but I've updated circle.c with some additional documentation at the head here. But the main thing I want to show inside these exercises is that the critical section, that is the shared memory that's used for the threads to communicate with each other, is basically completely centralized in this one variable here with the horrible name of var. That's probably the world's worst variable name, I think. And this variable var is going to be written to by the worker threads, and it's going to be read from by main when it kind of computes the totals here. And that's really the only way that the threads are communicating, only through this one variable. So you don't need to create new globals. You're not going to be using arguments. You don't need to use return codes. And that's basically the main restriction to keep in mind. You really only are using this one single variable as the only shared memory you need here. The only other thing that the worker threads really need to interact with is this kind of circle, the circle API, right? And that's going to return a value that you're going to be able to use and consume. So that's the problem. The first exercise is to implement this using mutexes, which are not new today, which you've used before. And then in the second exercise, you're going to go ahead and modify that to, instead of using busy waiting and mutexes, to use sleep waiting and condition variables. So I hope this is all clear. I have quite a bit of content in the lab guide. And of course, if you have any questions, feel free to post them in the appropriate Discord channel. Thank you very much and have a great day.